Warm welcome, everybody. Thank you for being here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have some mixed rate related problems. These are not all related rate problems, but they will involve somehow using a rate in order to answer our questions. More derivative style questions, but not exclusively derivative stuff, just rate problems. Okay, we're going to get started here, but first I'm going to cycle through the problems so you can see them for yourself. Here you can see the first question and the three parts to that question. Feel free to pause the video and check these out. Here's a nice little graph of the velocity. Feel free to pause the video, check out these questions. And we have some more questions that go with this. So here they give you a grid. You'll want yourself a grid, maybe draw yourself a grid that's like from -4 to 4 on the y-axis, and mostly just positive values for time so that you can indicate some important intervals. And then we have one last question, which also gives us a graph of the derivative of a function. And we're going to have to use that. Like I said, we're not just doing derivatives in this problem. We might be given a derivative and we have to use it. And we'll be asked some problems about, minimum, concavity, so on and so forth. All right, now as far as an approximate amount of time, I would say give yourself about 20 minutes, I think, possibly even more, because this related rates problem at first is so involved. In fact, I would say give yourself about 12 minutes for this first problem, and then maybe about 5 minutes for the second problem, just because we're only analyzing a graph visually. It's pretty easy to do. And then perhaps closer to like 7 minutes for this. So what would that be all in total? I guess it would be around 25 minutes. If you give yourself around 25 minutes, I think that's plenty. But whatever amount of time you take is okay. Try to do it as fast as you can. This is not an official AP free response problem, so it shouldn't be subject to the exact same limitations. Alright, and when you're ready, you can unpause the video, come back, and see how I did it here. Alright, we have a balloon that is 65 feet above the ground, and it's rising at a rate of 1 foot per second. So we can say that if it's rising at a rate, we can call this, and of course it's happening over time, we can call this dH dt. Maybe we should draw a little picture here. Meanwhile, a bicycle rider, which is directly under the balloon, is traveling on a flat road at a rate of 17 feet per second. So this will be like dx dt for the biker. Now let's draw this situation. I'm not going to draw a very good bike. There's our bike. And our bike is moving. Meanwhile, we have this balloon which is already 65 feet, but it is also going faster upwards. So we have dH dt, it's rising at 1 foot per second, which is not very fast, to be honest. We have this x value, which is increasing at a speed of 17 feet per second. Okay, so over time, we're going to have the dude like kind of far out here with the bike. And the balloon, of course, is going to be even higher. So there's 65, but the balloon is going to be even higher based on how much further it's gone, right? And this is going to be our x value, which is how far forward the biker is from being directly underneath the balloon. Okay, let's look at part A. Part A says, what is the distance between the balloon and the bicycle rider 3 seconds later? So let's imagine the triangle that is associated with this snapshot moment in time. 3 seconds later, the balloon is going to have traveled 3 extra feet upwards. And let's see, the distance between the balloon and the bicycle rider is represented by this diagonal. So this is 3 feet. That's the additional amount. And this is going to be 51 feet. There we go. So we can, of course, find the distance by using the Pythag theorem. So we're going to say that S is equal to 68 squared, S squared, plus 51 squared. Now, you might not recognize this, but it's basically just a 3, 4, 5 triangle. So this is just going to give us 85. If we were to do it, you might say more properly, I guess you can call it. What would we have? We would have 4,000. Whoops. Let's see, 9, 60, and 64 is 1024. So we would have something like 4624 plus 2601. Trust me, that's going to work out nicely. But I'm going to emphasize exactly what we should think of here in terms of using the Pythag theorem for its Pythagorean triples. So this is going to be 85 feet. That's how far they are. So 51 is 3 times 17. 68 is 4 times 17. So this is essentially just a bigger version of a 3, 4, 5 triangle. So this is going to equal 5 times 17, or 85. So knowing your Pythagorean triples can help you out. Also, being very fast at calculation can help. So at this moment, the bike and the balloon are 85 feet away from each other diagonally. Okay, great. Let's look at part B. How fast is the distance between the balloon and the bicycle changing 3 seconds later? So at the exact same moment, I think it's at the same, like, not 3 seconds later after the 3 seconds later. It's 3 seconds later, meaning the same moment in time. So now what are we looking for? We're looking for ds dt. ds dt. That's for part B. So we can use the Pythag equation, and we can actually use the same snapshot moment in time for any measurements that we might need. Let's just use the Pythag equation to say that in general, s squared equals 65 plus 1t, honestly, squared, plus 17t squared, right? If we take a derivative of both sides, we're going to get 2s ds dt, that's what we're after here, equals 2 times 65 plus t to the 1 power times 1, because that's the derivative of the height, plus 2 times 17t times the derivative of the inside, which is 17. Okay, now remember that this is going to represent these two things here, 65 plus t and 17t. These are going to represent the actual distances at that moment, which we already have. So since t is 3, this is going to be 2 times 68 times 1 plus, I guess this is going to be 2 times 17t times 17. So if I wanted to call this, what's that squared? That's just going to be 289. Oh, I was going to say 289t. But since our value is literally 51 here, we might as well just use the 51, right? Times 17 equals 2 times 85, we just got that from the last problem. ds dt, that's what we're looking for. Now, every term has a 2 in it, so I could just divide everything by 2 instead of making the numbers bigger. Let's make them smaller. And that means that ds dt is going to be equal to 68 plus, what's 51 times 17? Of course, that's 867. I know you knew that. Divided by 85. And so here we're going to have 935 over 85, which may not seem like such a nice number, but it is actually fairly nice. It's just 11. Right, so 85 times 10 is 850. If you add another 85, you get 935. So this is going to be measured in feet because it's a change of distance over seconds. That's approximately how fast this is going away. So that takes into account the fact that homeboy's riding the bicycle at 17 feet per second. So he's moving away pretty fast. The balloon is not moving up so quickly, but overall their distance is separating. Their separation is 11 feet per second just at that moment. Okay, units are important with related rates problems. Let's look at part C, kind of an interesting different question. How fast is the angle between the ground and the line connecting the balloon? So this is S, and this is flat ground. I'll just put flat, and I'll put S right here. How fast is that angle changing? Again, 3 seconds later, so it's basically at the same moment in time. Well, we need a description of the angle, and we need to relate two things that are changing, right? So how would we represent the angle and take into account everything that is changing? We could use the tangent ratio. So we can say tan theta, of course, is equal to the h, the height, over the adjacent, which is the x. So what we're looking at here is we're looking at how this angle is changing. Maybe I'll draw a little diagram. So at one moment we have that, but as time goes on, and this guy goes much further, you'll notice that this angle is obviously much different than this angle. Call this theta 1, theta 2, and as the dude keeps going out, that angle is getting smaller, right? Because the balloon's only going up 1 foot, but this guy's moving like way further forward. So this angle here is changing over time. It's getting smaller. That should make sense. Okay, now let's do the derivative of this expression. That was just a little diagram to demonstrate that each second we increase the opposite side a little bit, but we increase the adjacent side a whole lot more. So let's take a derivative of both sides. On the left side, we're just going to have secant squared theta d theta dt. That's what we're after, d theta dt. I should have also specified that when reading the question. So in the question, we're looking for d theta dt. And now we can go ahead and do that by taking the derivative, secant squared d theta dt. And then on the right side, we need to use the, we need to use the quotient rule. So we're going to have, however you've memorized it is fine, low d high x dh dt minus high d low h times dx dt all over the low. It's x squared. So we have information about pretty much everything here. X, h, dh dt, dx dt at that time. What we don't really have, but we can figure out on our way to solving d theta dt is this secant squared. So just remember that cosine is adjacent over hypotenuse. So secant theta is going to be hypotenuse over adjacent. I'll put hype so that we don't think it's h, like the height. Put hyp so we know it's hypotenuse. That means secant squared theta obviously is just going to be this squared. So if we take the hypotenuse and the adjacent, we know that the hypotenuse is 85 and the adjacent is 51. which is just 5 over 3 squared. That's 25 over 9. Okay, so we can plug in our information now to say that 25 over 9 times d theta dt is equal to, let's just plug our stuff in, x times dh dt minus h. At that moment, it's 68, right? 3 seconds later, it's gone from a height of 65 feet in the air to 68 feet in the air. And then times 17 all over 51 squared. So the really interesting thing that I would like to do to make this work a lot easier, it might look like a bit of a mess, is I would actually like to replace this back with just 85 squared, rather 85 over 51 squared, which really is just 85 squared over 51 squared times d theta dt. Now, why would I want to do it like that instead? That's because I'm going to be able to multiply, I guess I have to multiply these, so what is that going to be? 1156, I believe. Let's see, 289 and 289 is of course 578, and 578 times 2 is, yeah, looks good, 1156 over 51 squared. Now here's where the magic is. I'm going to multiply both sides by 51 squared. And that's going to easily get rid of this denominator. So now we just have 85 squared times d theta dt essentially just equals 51 minus 1156, which is going to be a negative 1105. Yeah. And then we're going to divide on both sides. So that could look a little messy. Negative 1105 divided by 7,225. That's 85 squared. If we want to divide everything by 5, we can get negative 221 over 145, basically. Oh no, oops, 1445. Yeah, that should do it. I don't believe we can reduce this anymore because the top is not divisible by 3, not divisible by 9, not divisible by 7, not divisible by most of these numbers. I mean, I know 11 doesn't even work, actually. So yeah, I think I would leave it like this. If this were on a calculator problem, of course, you can get more specific, you know. And if you really want a decimal, feel free to get a decimal. So this would be like 0.1. Let's see how much else we have here. So that'll be 765. Add a 0, and this is about 5. So 0.15 if you really, really want a value. 1, 2, 2, 5. So this is going to be 425. And there we have, it's about 3. I mean, it's technically a 2. We can't get 3 in there. But if we get 2, that's going to be 2890. And when we subtract that, we're going to have 136. So see, we're very, very close here. That's going to be a 9. So if you want to say it's approximately 0.153 radians per second, and that is a negative because this angle is, of course, decreasing, that would be correct. Presume I didn't make any calculation errors, which is totally possible. You know, I'm not perfect. All right, that gives you an idea of how to solve this related rates problem. I really liked that problem because they asked you, even though they asked you about the same exact moment in time, they ask you some different questions about it. And in the last one, you have to use the quotient rule. There's no way around it because all of these things are changing. The theta is changing, the h is changing, and the x is changing as this guy is biking. I don't know if he's biking fast. 17 feet per second, is that fast? I don't know. Probably faster than me. Okay, let's look at the next problem, which gives us the graph of a rate. This shows us the velocity. So at time t equals whatever, we have a certain speed, a certain velocity, rather. Any positive velocities are when we're going forward. So these moments in time are going forward. When does the particle move forward? It's going to be great. So this is going to be when v is greater than 0. So we're going to say that from 0 to 1, union from 5 to 8, this thing is moving forward. When is it moving backwards? That's when v is less than 0. So that's going to be covered when t it goes from, not from 2 to 5, from 1 to 5. And it changes direction, so we can say positive to negative, or negative to positive. So that's going to happen at t equals 1 and at t equals 5. When is it at rest? This is going to be, of course, when it's at 0, and then also from 8 to 10. So this is when the velocity equals 0. Very simple. When does the particle speed up? Now there's two ways to look at this. First of all, you need to know that the speed represents the absolute value of the velocity. So whether or not it's positive or negative just tells you the direction. It doesn't tell you the speed. You can be going 10 miles per hour in any direction. When does it speed up? When does it slow down? So speed up means that this is getting bigger. Of course, that means getting smaller. But the better way to analyze that on a graph of the velocity, the better way to write that, speeding up, velocity gets, let's put this in bold underline, further from 0. And on the other hand, slowing down means our velocity gets closer to 0. So if we just look at that, it's pretty easy to tell when it's going closer to 0, right? When is it going towards the x-axis versus when is it going away from the x-axis? And then here again, it's going towards the x-axis, and it's going away, and it's going towards. See that? So the black moments are when it's getting slower because the speed and the velocity, therefore the speed is going to 0. So this is going to be from 0, speeding up, sorry. From 1 to 2, it's going further, and then from 5 to 6. On the other hand, it is slowing down when we're getting closer to 0. That means t is on the interval from 0 to 1, or the interval from 3 to 5. I guess I shouldn't just put commas, I'll use unions. And then it's slowing down again from 6 to 8. Basically anywhere it's not speeding up, it's slowing down or resting. So from 8 to 10, it's not doing squat. Okay, part D wants us to graph the particle's acceleration, and we want to identify when the acceleration is positive, negative, or 0. So remember that this is the derivative of the velocity with respect to time. So the slopes. And we can easily plot the slopes by just checking the slope of these line segments here. So this first line segment goes down 4 over 1, down 4 over 1. That's for the first 2 seconds. So we're going to be at negative 4 for the first 2 seconds. Then, since we have sharp corners here, we're not going to have a continuous derivative. There are going to be some gaps, some jumps. then all of a sudden it's 0 from 2 to 3. Object is not accelerating. Then we have a positive slope. Seems to go up 4 over 2, or in other words, up 2 over 1. So we have a positive slope of 2, and that's going to last until time 6. That's for 3 seconds. We go up 2 over 1 second, up 2 over 1 second, up 2 over 1 second. That's 3 seconds. And finally, we have a slope of down 2 over 2, so that's -1. And that's going to cover from 6 to 8. So if this is -2, we'll just call this -1. Why not? And then we have a slope of 0. There we go. That's the acceleration. So if we want to identify when the acceleration is positive, negative, or 0, we can just do this. We can say a is greater than 0. Let's use a different color for that. Let's say a is greater than 0 on the interval from 3 to 6. We can say a is less than 0 on the interval from 0 to 2, and also from 6 to 8. And then we can say a is equals to 0 on the interval from 2 to 3, as well as the interval from 8 to 10. Okay. Now, what is the particle's fastest speed? It's a good question. Well, we should just look at the velocity graph, I think. It's easiest to take a look at that. So what's the most that this speed is? We see that the velocity is a +4. It's pretty fast compared to all this. And then we have a -4. Those are the same speed. They're just opposite directions. So we would say 4. Do we have units here? We don't have units on the y-axis. So we can just say like meters per second or whatever. 4 units per second. And it's not positive or negative. Speed is not positive or negative. Or I should say speed is always positive because there's no direction associated to it. Okay, and let's look at this final problem, which again gives us a rate, it gives us a derivative. This graph is the derivative, so we're going to probably have to use some fundamental theorem of calculus. I see that we're given areas of these regions underneath the curve, and this region is an area of 2. Notice it's negative, so I'm actually going to put some red lines there. Okay, and this should help us out a lot. Let's look at the questions. Where is the local minimum? I think they mean of the original function, by the way. OG function has a minimum when f prime goes negative to positive. So let's just look at the locations when this graph goes negative to positive. It's positive, 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 0, positive, 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 0, negative from 5 to 7. So that's when we're going to have some kind of a minimum here, when the derivative goes negative to positive. So we're going to say at t equals 7. I don't know if there's no time associated, so we can just say when x equals 7. Where is it at? It's when x equals 7. Now, if they want us to find what it is, they will say what is the minimum rather than where. Where is the absolute global minimum? So here we have to be a little bit careful. We're given an interval. We're given an interval, so this is going to go from 0 to, what was it, 8? Yes, from 0 to 8. So we have to consider f of 0. We have to consider f of 7, any critical points actually, so f of 2 and f of 5 as well. f of 7, and of course f of 8. Now, if we remember the fundamental theorem of calculus, we'll say that the integral from a to b of f prime is simply equal to f of b minus f of a. So therefore, we're going to have the smallest value wherever we get the fact that the integral there is smallest. So assuming that they all have the same starting value, we could just say that f0 is the integral from 0 to 0 of f prime, which is just 0. That's pretty low. That's going to be our minimum, and I'll show you why. Because f2 is going to be all of this area. So f2 is just going to be the integral from 0 to 2 of f prime, which equals 2. That's not a minimum. f5 is just going to be the integral from 0 to 5, which is also, a decent value. It's going to be 2 plus 3.5 because it's all of this area here. So that's not going to be a minimum value. f7 is going to be a local minimum, but it's still not going to be a minimum, because if we add all the positives and subtract the negative area here, we're just going to end up with 3.5, which is lower than 5.5, but it's not the lowest. And then lastly, we have f8, which is only going to add more area, so there's no way that that's the smallest. So really the smallest is going to be f of 0. Where is the absolute minimum? At x equals 0. Okay, part C. Where's the function? Again, I think we're talking about the original function. Where is it concave up and increasing? So this means that we want the second derivative to be positive. And this means that we just want f prime, the first derivative, to be positive. So we can easily track that because f double prime is the slope of f prime, which is slope of the given graph. Pretty easy. Whereas f prime is the actual y value on the given graph. So we want the actual y value to be positive, and we want the slope to be positive. Let's take a look at where that happens. In fact, I'll erase some of this stuff now, just so that we have a little bit better visual. We want the graph to be positive and the slope to be positive. So not any of this. This looks good. This is going down. We don't want any of this. This is negative. We don't want any of this. But this is positive and going up. So we're going to take those two intervals. We can say that this happens on the interval from 2 to 3 and the interval from 7 to 8. And that'll do it. Okay, now the more involved part of this problem, where you have to actually do a little bit of calculus. It says g of x is f of x squared, and they give us the initial condition f3 equals 8. They want us to find the slope of the tangent line, just the slope of the tangent line, at this value. So you don't have to write the equation of tangent line, y minus y value equals m times x minus x value. You just need to take the derivative and find the slope. So we basically want g prime of 3, okay? So if g of x is f of x squared, that means g prime is the derivative, which is going to be 2 times f of x. That's why we needed the initial condition, times f prime of x. That's where we get from the graph. So g prime of 3, this is actually much easier than I thought. 2 times f of 3. Again, they give us that value, not on a graph, but they give us the description of that value, times f prime of 3, which is just the y value. Don't get confused. Don't look at the slope of the graph, because the graph is f prime. So this is going to be 2 times 8 times the value at that moment, which I think they specify is like 2 or something. Let's double check. Yeah, 3, comma 2. So this is f prime of 3. It is 2. So therefore the slope of this is just 32. Okay, so that's just a little mixed bag of some rate problems and, free response style questions that could be asked about it. I would say that this graph is very likely to come up on the AP exam. A little less likely to make you graph the acceleration, but they totally could. So look alive for that. And then, of course, we have everyone's least favorite section. Maybe not least favorite, but one of the tougher sections that challenges a lot of people is the related rates section. So keep practicing. I know you have a lot of work on your plate, but the more you practice and the more consistently you practice every day, the better it will stick. That's enough blab out of me today. I'll see you guys next time in the fourth.